Hello everyone. Let us start today to talk about a very important topic in the control design and analysis of control systems, and that's stability. Stability is fundamental property, and we will write this with this thick line. Stability. Okay, and what we can say about stability of the linear system. So we know that our linear systems were given as x k plus 1 phi of x of k, providing that u of k is equal to 0. So we can determine pretty much what happens with the evolution of the state if we initialize the state at a certain initial condition and we let inherently to evolve with the dynamics of this phi of k model dynamics representation. In other words, we can have the following sequence that essentially shows that the system diverges as it goes, as k goes to high number. Or we can have a system that starts from initial condition and then attenuates to 0. In other words, for these green dots we say that system is unstable, and contrary to it, for these yellows we say the system is stable because all these, the evolution of the system states converges to either 0 or to some fixed value. In this case, everything has to converge to 0 because this is just a LTI system, linear time invariant system dynamics. Therefore, how do we determine that? So the easiest way to determine that is by direct evaluation or calculation of evolution of the states. So if we have a f of x of k, we can easily obtain that x of k is nothing but phi of k x0. So this is the solution of the above equation. So, but how do we calculate this phi of k? Because we essentially know that phi is a matrix, and then we will have a matrix multiplication on the kth order. So at k goes to infinity, we have to conclude what happens with x of k. So in order to do that, let us just recall what is the notion of the stability in the continuous system dynamics. So here we claim that on this side we were stable when eigenvalues of the continuous system representation x dot equal a of x were negative, so lambda was less than 0, and unstable here when the eigenvalues were greater than 0. In the same way, we have for the discrete system. If the base of the lambda is greater than 1, and lambda is an eigenvalue of phi, then we will have the system is unstable. In other words, take any number with the base greater than 1 and start multiplying that, and you will obtain that the system, that state will essentially diverge. In other words, for lambda 1 is unstable, and inside is stable. So whenever the lambdas of phi are inside, stable. Okay, so this is stable. And how do we find out now about that? There are several ways. Let us consider one of the simplest ways. Let us consider that we find transformation that is a simple transformation x equal t of z, such that we have that t z k plus 1 a or phi t of z. We multiply this with the t minus 1 with this transformation, and we obtain that this new system becomes z k plus 1 equal t minus 1 phi t z of k, while 0, 0 is t minus 1 x of 0. Okay? In other words, this expression now becomes matrix D, that is just a matrix of diagonal entries of lambda. Lambda 1, lambda 2, and then lambda m. System is of the m size. So all other entries are 0. If we have that, we directly can find out that z of k is going to be lambda 1k, lambda 2k, and lambda mk power k z0. So if we have that, we have directly resolved the issue of the stability of the eigenvalues. Okay, now let us look at the way how we can calculate this transformation t. So obviously, if we have a transformation, we can easily obtain direct knowledge about the system stability by checking the eigenvalues of the matrix phi. But in order to obtain these eigenvalues, we have to find the transformation t, and let us do a simple example. In this case, let us consider as follows: A to be matrix, so we have a x of k plus 1 equal a x of k, and A to be matrix 1.5, simple example, 1, 0, 0.5. And first we want to find the eigenvalues of this matrix, and eigenvalues are obtained from the characteristic polynomial lambda 1 minus 5 multiply lambda minus 0.5, such that the first lambda is 1.5 and the second lambda is 0.5. Okay, by doing this we already find out this expression, and we already determined the lambda 1 and lambda 2, and we see that the system is going to be unstable. Okay, however, we also want to find this transformation t, and we are going to demonstrate how this is obtained, because sometimes we want to find what is the value if the system is stable, and what is the value of the state that we can calculate by transforming this into appropriate form and utilizing these when we have a large scale matrices. In other words, for the lambda 1 there is associated vector v1, and we obtain that as a lambda 1I minus a v1 equals 0. If we rewrite this equation, this will become as follows. 1.5, 0, 0, 1.5 minus 1, 1.5, 1, 0, 0.5. Okay, and here is the vector v1 and equals 0, 0. So what is that vector v1 that is associated with the lambda 1? Let us find out. When we subtract 1.5 by 1.5, we obtain here the following expression. And this is 0 minus 1, 0, 1. v1 equal 0, 0. So this v1 is a vector 2 by 1. In other words, we are saying that if v1 has two entries, let's say v1 hat and v2 hat, what these two entries have to be to satisfy this equation? We find out that v1 essentially can be any number, because 0 multiplies v hat 1 minus v2 hat equals 0. So v1, any number. Interesting, any number. This is quite interesting that we have this freedom. And let's say that v1 is 1. Let's assume that is 1. Let's take 1. So we have that v1 hat is 1, 0. In the same way, for the lambda 2 v2, we have a lambda 2 I minus a v2 equals 0, 0, 0. So this will lead to the following expression: 0.5, 0, 0, 0.5 minus 1.5, 1, 0, 0.5, and all of this multiplies v2 equals 0, 0, which now leads that after we calculate this, leads to the following equation: minus 1 minus 1, 0, 0, v2. Okay, and therefore we conclude again that v2 has to be 1 minus 1, because 0 multiplies v2, v1 hat, 0 multiplies v2 hat. Essentially, v1 hat and v2 hat can be anything, but here we have that relationship between v1 hat and v2 hat is that they have to be in this form: v1 hat minus v2 hat equals 0. So if v1 hat is equal 1, v2 hat has to be minus 1. Okay, that's how we got this expression. Again, it's a freedom. We could take any other number. And let us finally demonstrate what we have, that if x here, k plus 1, as we did previously here, is going to be transformed into zk plus 1 t minus 1 a t z 0. Okay, let us calculate this expression. And here we have following 1. Where is that? 1, 0 is our t. 1, 0, 1, minus 1. Okay. Therefore, d becomes 1, 1, 0, minus 1 inverse multiplies 1.5, 1, 0, 0.5 and multiplies 1, 1, 0, minus 1. Okay? Let us show the following trick that we know that A, B, C, D is going to be 1 by AD minus BC. D and A, you just swap that and you put minus B minus C. Okay, this is for the 2 by 2 how we get the inversion of the matrix. In other words, we will get the following. We will get a minus 1, that is from the determinant, and we will have a minus 1, minus 1, 0, 1. Let us calculate these two matrices, and this is going to be 1.5, 0.5, and this is 0, minus 0.5, and finally these two matrices, when we multiply, becomes 1.5, 0, 0, 0.5. We can check here 0.1, these multiply this, give this element. Finally we get the D. So this is the D. Okay, so we see that easily by using this transformation we can calculate the D, and now we can obtain the evolution of the system in Z and transform it back to X. So this provides us with the insight how to find out what is the evolution of the system and whether the system is stable or not.